Good morning. We are group number 3. I am Radha Nafre along with my fellow teammates Arya Thomre, Arya Shevare and Nachiket Davalkar. We are here to explore how algebraic structures like various groups, fields, lattices can be applied in the field of cryptography. But first, let us start by understanding what exactly is cryptography. In today's world, whether it is online commerce, international relations, or simply email communication, the encryption and decryption of data is essential to the security of everyday life. Thus, cryptography is the study of encrypting and decrypting messages with the goal of sending a message so that only the person intended can understand it without any unwanted eyes. Now, of course, to do this efficiently, it is important that there is some structure behind the process rather than just random procedure. And this is where algebraic structures and coding theory are applied in cryptography. Now, we have chosen 8 encryption and decryption schemes to present in our poster, which make use of the following algebraic structures like groups, fields, lattices, and vector spaces.
The next topic is groups. Groups are mathematical structures that satisfy certain properties such as closure, associativity, identity element, and the existence of inverses. The first use of groups is the Diffie-Hellman key exchange. The Diffie-Hellman key exchange protocol relies on the properties of certain mathematical groups. The Diffie-Hellman algorithm allows two parties to independently generate a shared secret key without exchanging the key itself. The algorithm is as follows. First, the party agrees on a public prime number and a base generator. Second step, each party independently selects a private key. And the third and the last step is that they exchange public keys and perform computations to derive a shared secret. The applications of Diffie-Hellman key exchange are secure communication protocols, virtual private networks or VPN, wireless security, email encryption, and digital signatures. The second use of groups is zero knowledge proofs by Schnorr and Guilleau-Quisquater. Zero knowledge proofs, such as the Schnorr and Guilleau-Quisquater protocols, utilize mathematical groups. Zero knowledge proofs allow one party to prove to another that they know a certain secret without revealing the secret itself. The algorithm is as follows. The Schnorr identification protocol is a zero knowledge proof that allows a prover to convince a verifier of knowledge of a discrete logarithm without revealing that algorithm. The Guilleau-Quisquater identification scheme is another zero knowledge proof protocol which is extending the concept of the Schnorr protocol. The two applications of zero knowledge proofs are first, key exchange, which allows two parties to establish a shared secret without revealing anything, and second, blind signature. Blind signature is a type of cryptographic digital signature in which the signer is unaware of the content being signed.
Next up, we have the use of fields in cryptography, which brings in Reed-Solomon codes. Reed-Solomon codes are a group of error correcting codes. So basically, when we transfer data over network, the data may get corrupted due to network problems. So Reed-Solomon codes help in recovering these corrupted messages. These codes are based on finite fields, or more specifically, Galois fields. A finite field has the property that arithmetic operators like addition, subtraction, multiplication, and division on field elements always have a result in the field. Reed-Solomon codes, which have two parts, an encoder and a decoder, need to carry out these operations and hence make use of fields. Another very interesting encryption and decryption scheme that makes use of field is the Shamir's secret sharing scheme. Imagine there is a secret like missile launch codes or passwords to huge money transactions, which require multiple people to confirm before applying a key. An approach to solve this is to divide the secret into parts and give it to each of the people. But that is not very efficient because that gives away a part of the secret. Thus, we use secret sharing algorithm created by a person named Ali Shamir. The secret is imagined to be a point and its shares are imagined to be a point on a very secret curve. To carry out arithmetic operations to encrypt the secret, finite fields are used here.
Now let us see how lattices are used in cryptography. Lattice-based cryptography is a type of cryptographic construction that relies on the computational hardness of certain problems associated with the mathematical structures known as lattices. Lattices are geometric structures formed by an infinite grid of points in n-dimensional space. Now let's see cryptographic scheme. Cryptographic schemes refer to a systematic design of structures for securely exchanging information between parties in the presence of potential adversaries. These schemes use cryptographic techniques and algorithms to achieve specific security goals. Lattices are used in cryptographic schemes, particularly in lattice-based cryptography, to provide security against classical and quantum adversaries. Lattice-based digital signatures schemes use the properties of lattices to create secure signatures. Lattice-based key exchange protocols allow two parties to agree on a shared secret key over an insecure communicational channel. How it works? Ring LWE and related lattice problems are employed to ensure that an eavesdropper, even with the access of exchange information, cannot easily compute the shared secret's key. Moving on to post-quantum security. Post-quantum security. The lattice-based cryptography is considered post-quantum secure, meaning it is believed to be resistant to the attacks by quantum computers. The underlying lattice problems are not known to be efficient solvable by quantum algorithms. Public key encryption. Lattice-based cryptography provides the foundation for constructing post-quantum secure public key encryption. In lattice-based public key encryption, the public key is a lattice-based structure and the security relies on the difficulty of lattice problems. In summary, lattices are used as a mathematical foundation in various cryptographic schemes, especially in the emerging field of lattice-based cryptography. The inherent complexity of lattice problems form the basis for the security of these schemes, making them resistant to attacks from both classical and quantum adversaries. Thank you.
Application of linear script analysis. It is used to design and analyze the cryptographic algorithm. It is used for research and development purpose. It is used in algorithmic design. In short, linear analysis is powerful technique for analyzing. Okay, so let us discuss about error correction. It is an important aspect in various fields like information theory, code theory, and communication. Here are some important points about error correction. The purpose of error correction. It is used to ensure accuracy and integrity of stored data. Error correction occurs due to data transmission or storage. Application of error correction. It is used in telecommunication, networking, data storage, and etc. It is employed in telecommunication like CD, DVD, QR code, and etc.